Hi guys, and welcome to this video. Finally, I'm trying to make some very compressed version, and yes, this is very awkward. Talking to myself and all that. So let's just go to the point. Well, what is this video about? It's about the covariant and contravariant indices, and why is there a difference between them, and why do you have to be careful about it. Okay, so I tried this video for a couple of times and it always turns out to be very long. So let me just get straight, let me just get straight to the point. The point is that what you thought, how you represent a vector in terms of its components, vi, ei, is not the only way. It is, looks like the only way in three-dimensional or two-dimensional Euclidean, my god, my handwriting is awful, Euclidean space, which is orthogonal. Okay, so for a basis in which these basis vectors obey the following rule. This is a unit matrix. It's not a chronic. I mean, it is a chronicker, but I don't want to write it as a chronicker. Okay, so what does this mean? It means that if I draw a coordinate system like so, with axis x1 and with axis x2, and I point my basis vectors to point along the directions of these axes, so there is a right angle here, then the vector which I draw here is going to have components v1 and v2. Okay, now we're going to change something. We're going to change one by one. We're going to change everything. First of all, we're going to lose the arrow. This is number one. What I mean by that, I mean v is not going to be v, it's going to be just v without an arrow, vi, ei, and also e is without an arrow. Why is that? Well, because arrow is just a thing that helps you remember that what this is called an abstract vector, and its existence is independent on the basis that you choose and components or coordinate systems or whatever. It's the thing itself. It doesn't know about any basis, it doesn't care about any basis, it just exists. The only thing that it does care is its length. This is like its ID. Okay, and this length, we're also, of course, we're going to lose the arrow, and we're going to calculate in some basis, chosen basis, let's say this one. How do you calculate? You make a scalar product between these two, between the vector and itself, and what you get is a double summation vi, vj, ei dot ej. Now pay attention that I have basically used vi, ei, and then again one other thing like that, but with a change index. And this is very important. You change an index and then you know what are you summing with. This guy is summed with this guy. This guy is not summed with something from here. Okay, and that's very important. So keep that in mind. Changing or relabeling the indices is a very powerful thing and necessity when you have many indices to work with. And so now this scalar product here is just a unit matrix, right? What does this unit matrix do? Well, it picks up only components which are the same, only those component I which are the same as j. So in other words, this just becomes vi squared. And this is v1 squared plus v2 squared, right? But I would like to write this in a matrix notation. So I would like to write this as vi. No, I will not write this as in matrix notation just yet. Okay, just remember that this is a unit matrix, and this matrix is what makes the square of the length be calculated like a Pythagorean theorem. Okay, that's one thing. Now the second thing is related to the way that we write indices. And this is where the fun starts. Okay, now you're going to learn why contravariant is called contravariant. and what does it mean. So suppose you take a basis vectors and change them by 2. You just rescale them by 2 EI. Okay, and the question is, what happens with EI component? Sorry about that. What is the VI prime component? And the answer is, well, take a look at this abstract vector on one side and take a look at on the other side. The primed one and the unprimed one have to be the same because it's an abstract vector and it doesn't care about the coordinate system. So on one side you have one side you have VI EI, on the other side you have VI prime EI prime. And if you change VI to VI prime, I'm just going to do like this because I want to try to save writing, and luckily this is a video and you will use pauses and rewinds and that's very, very useful, and we don't have that in class, so use it here. So this is just 2 times VI, and you see that this guy actually has to be VI in order for this to be equal. So from here it follows that VI prime is equal to 1/2 of VI. And now what you do, you compare these two transformations. You compare this transformation with this transformation, and you see that there is a 1/2 here and there is a 2 here. What do I want to say? I want to say that if EI varies in some way, so they vary in this way that they are multiplied by 2, then the component VI, they vary in a contra way in order to cancel that change and leave the abstract vector invariant under this change. Okay, so if they vary in a contra way, then we say they contra vary. Contra vary. Ta-da! This is why they're called contravariant components. And in order to distinguish without writing in words, hey, this component is contravarying with respect to this other basis vector, you write VI with an upper index and you call it contravariant component. Not a contravariant vector, contravariant component. And yes, we do call them contravariant vectors, but it's just a misnomer. And it's okay to call it contravariant vector as long as you say that a vector as an object is independent on components and the basis. So contravariant components. Okay, so now we have this notation change. There is one more notation that we're gonna do. I'm gonna change the slide now. The one other change that we need to do, did I put numbers here? 1, 2, okay, let it be 3. Number 3 relates to summation. And yes, I do mean summation convention by that. So given the vector that we just had written in VI upper components EI lower VI upper index EI lower index, by what we mean that this is invariant implies that it has to have one upper component and one lower component if it is comprised of indexed quantities. And because of that, there will always be in a summation one upper index and one lower index if there are some pairs of quantities summed. And that is why you do not need to write a sum. This is all there is to it. There is no like magical thing happening. It's just a convention because it makes things simplified, and it implies that this whole thing, the abstract vector, is invariant. Okay, number 4 is also one other useful thing which kind of follows from here, is that you can attribute to EI a row matrix, and you can attribute to VI a column matrix, so that you can write the vector V as EI row times VI column, and this just evaluates to one number. It's not a number, it's a vector, but it's a one component, so to speak. E2 V2, okay, and this is invariant. So this gives you a motivation to call these guys as well, to call them a vector. We just call them like that because of a misnomer. on GR. So they're not vectors. These are vectors. The abstract things are vectors. But in physics, usually you just call the vector component, the set of vector components, you call them as a vector. And this is okay if you have in mind what we learned before. Okay, so what we can conclude from here is that indexless object, like a scalar or an abstract vector or an abstract tensor and whatever you're gonna see, is invariant. And it necessarily, so it's either invariant because it's a scalar product, so it's a scalar, or it's invariant because it's a abstract vector. So it assumes that it is made of or expanded in components whose transformation is compensated by the corresponding pair with an opposite index. So under a change of basis, that's what I mean by transformation here. Under change of basis. Okay, it works for any kind of transformation, not just rescaling. We just use the rescaling to rescaling by 2 just to make an example. Yeah, okay, so that's that. And now we can use all this notation to represent the length squared. And the length squared is just going to be ei dot ej, so it's coming from v dot v, right? It's ei dot ej, vi vj, there's a sum over I, there is a sum over j. This guy evaluates to a unit matrix, and this is just unit matrix ij, vi vj. And you can use this row and column matrix notation to represent this color product, and it's going to look like this: v1, v2, different color, matrix 1 0 0 1, v1 v2, and this is just a rule that says that you calculate this distance as using the Pythagorean theorem. In distance I mean the length of the vector. Yeah, and this just evaluates to be v1 squared plus v2 squared. I'm not going to write it again. Okay, that is very interesting, and this is all. This is what we learned to use in our everyday life. However, our everyday life also includes crystals, and crystals are what? Crystals are ordered structures of atoms. They have some symmetries that is very nice to study, and it turns out that if you use orthogonal coordinate system such as this one, please be straight, okay, such as this one with basis vectors having a 90-degree angle between them, it's not really useful to represent atoms in such coordinate system, because you see the atoms have patterns of repetition in three or more directions, and you can represent these patterns of repetition along the axis that you will introduce, which do not have to be under the right angle. And what I mean by that is that instead of writing these axes like so, you draw them like so. And if you think that this is not a legitimate way of writing a coordinate system, well, you can always ask, how do I represent vectors in this coordinate system, and check if I'm right or wrong. Let's just leave one atom. The angle between these is theta, and this atom is with a distance from the origin described by the vector v. And the question is now, what are the components of this vector in this basis? This basis now has a rule which is not a unit matrix, which is so the scalar product rule, which is not a unit matrix, but it actually results into something different. So this is 1 only if I is equal to j, but if I is not equal to j, then it's cosine theta. And yes, you can write this as a matrix. This is just 1 cosine theta 1. Okay, now we come to the very fun part. So we know what basis is, but we don't know what components are. And this vector does have some components because you can just write it in such a way, right? But the thing is that we're going to calculate the length squared without knowing how to draw these components. We don't know how to draw them. And we're going to have to figure out how to draw them. So what do you think? Do you draw them like this, orthogonally to the axis, or you draw them like this, parallel to the axis, or you draw them in some other third funny way? So think about it for a moment and think about a way to figure out what is the correct projection of this vector into its components. Okay, have you thought about it? So let's try to use the best tool that we have, which is always something invariant. And I will expand this VI into VI and VJ components with this unit matrix, with this matrix here, which is not a unit matrix anymore. This will turn out to be simply V1, V2, 1, cosine theta 1, and again V1, V2. Now I write them with green and upper indices because I know that my basis is given with lower indices, so I have to have contravariant components. So the question is actually how are they projected in a basis which is non-orthogonal. Let me just write that this is non-orthogonal because theta is not p half. If theta is p half, this just becomes an orthogonal coordinate system that we had before. Okay, so what does this evaluate to? This evaluates to V1 squared plus V2 squared plus 2 times cosine theta V1 V2. And now we see that exactly this is the guy that just makes our life more difficult. It's not anymore a Pythagorean theorem. So this rule here is not Pythagorean theorem anymore. It's something else. So how do we figure out what this is? So what does this remind you of? What does this formula remind you of? If there is something ringing a bell, just go and Google it for a minute or something and then come back. Okay, so what reminds me of is something called the cosine theorem, or the law of cosines. Law of cosines. So how does the law of cosine work? Well, you have a triangle which is not the right triangle, but it's something else. There is a gamma which is different than 100, different than pi half, and you want to calculate this C length in terms of A and B. So C squared is A squared plus B squared minus 2AB cosine gamma. This is the law of cosines. And if you compare it with this equation that we have here, it seems like gamma is pi minus theta if you attribute A to V1 and B to V2 and C to the length squared, C squared to the length squared. Okay, so this is very interesting. What does this mean? This means that this triangle actually does not look like that, like this. it looks like this, where this is pi minus theta, or this is here is theta, so this is A, this is B, or this is V1, and this is V2, and this is C. Nice. So now you just transfer this photo, this graph, into this picture here, and you will see that the green components actually fit exactly to be those which are projected in a parallel way to the axes. Axis? Oh, never mind that. So V1 and V2. Right. But the thing is, maybe to some of you it would be more natural to draw components like this. I mean, you know, why not? Well, why not is the answer to why not is this here, what we just did, because if you choose to represent your so if you expand your vector in a basis, then these components which are supposed to be contravariant in order for the abstract vector to be invariant, then it follows that this is the rule. And if that is so, even if that is so, I can still ask, what is the meaning of these blue components? Why cannot I project in such a way? So I'm just gonna delete this part over here because we need the picture, and I don't want to get a new slide for that. Maybe I don't want to, I don't know. So we know that this is theta here. Okay, and now the question is, what are these blue components? Now I'm going to do a spoiler here, and I'm going to say, okay, well, this is something which I need to write in a different way. So I'm just going to write it with a lower index. It doesn't mean anything for now, but you expect what it's going to mean, but let's just pretend that we don't know what does it mean. So just write it in the opposite way. And the question is now, okay, how do I calculate these components? Suppose that I just want to express this vector in terms of these components. So what is it? And I want you to pause now and try to figure out, this is just from the geometry of these triangles, you will figure it out. What is this blue component in terms of the green component? So what is V1 and what is V2? So pause the video now. Pause it. Okay, I'll assume you pause it and you try it on your own. So what do we have? We have that this guy plus this guy is equal to the blue guy. This is perfect. So what is the small guy? Well, the small guy, the first one is, let me just draw this in green, maybe it's better. The green one is just V1. And then there is a plus, and now we have to figure out what is this other one. Well, this other one is, since this is V2, this is just going to be V2 cosine theta. Right, V2 cosine theta. And the second one is the same thing, just the other way around. V1 cosine theta plus V2. Aha, so now we have expressed these blue components in terms of the green components. This is very interesting. So even though we didn't expand the vector in terms of the blue components, we have found a relationship between the green ones and the blue ones, such that, you know, if someone wants to express and calculate the vector in terms of blue components, he might as well do so. But before that, I want to note something very interesting. Take a look at this and write it as a matrix, in a matrix form. So write it as, you know what, write it as a row matrix. V1, V2. Okay, so what is this? This is nothing else than V1, V2, and then times such matrix. So we just figure this out just from the way of writing the system of equations in a matrix form. Right, but take a notice this. Look at this one and look at this one. They're exactly the same. And then we say, whoa, wait a minute, I can write the v squared, the length squared, as blue ones, yes, I'm doing this instead of typing because I'm lazy, blue ones times the green ones. What does this mean? Well, this means that, doesn't mean this, sorry. Undo. Let me just write it. So what does this mean? This means that blue and green components actually work together. So this is equally a valid expression as the one that we had only in terms of green components, except that this one has a mixed blue and green components. But now we have achieved, this is not 1, this is 2. Now we have achieved something very interesting. Remember how we said that if something is invariant, then it has to be a sum of some pairs which have one upper and one lower index. So it's a sum of pairs with one upper and one lower index, and the sum is assumed, so you don't have to write it. Okay, well, this has exactly the same form. It looks like it's a sum of blue components with a lower index and green components with an upper index. So this is like a backwards wisdom why we chose to write the blue components with a lower index. They have a meaning because they have that kind of a meaning because they appear in the sum in such a way that there has to be one upper, one lower components. Now you go one step back, one more step backwards and say, okay, if that is so, then these blue components, I kind of expect them to transform, to vary. I expect them to vary along with EIs, with the basis vectors, because in this sum here, they have the same role. If the contravariant components, if the green components change, then the blue components have to change in an opposite way. Or if the blue components change, if they vary, then the green components have to contravary. And this is why you call these blue components then, because they are varying along, or they co-vary with the basis vectors, then these are then called covariant components. Okay, nice. So we have contravariant and covariant components, and they have a meaning. But there are a few things that I should mention. I should not rush. The first thing is that if you name covariant and contravariant components and you want your abstract vector to be expandable in both covariant and contravariant components as well, then there has to be some sort of basis, right? There has to be some sort of basis which you expect is going to have some sort of vectors with upper index, in terms of which v can be expanded as vi ei. So this is the question mark. So I may talk about this at some point later on, but for now on, for like the purposes of what we're doing here, this is not important to think about right now. You may think about it, you may figure out how to draw them in this coordinate system, and so on. But what I want to focus now is to try to finish this video and not take it long enough to focus on this matrix here. So this matrix appears in two different things. It appears as a relationship. Maybe I don't know how to. So it appears here as a relationship between the green ones and the blue ones. That's one way where it appears, and the other one is here, telling us this is not Pythagorean theorem. So this is it defines the scalar product. Okay, let me delete what is unnecessary. So this is not Pythagorean theorem. This is not important. This is also not important. It doesn't matter now. We figured this out. So the only thing that is important is this and this. It appears in two ways. So let's give this matrix a name. v squared is equal to ei dot ej vi vj, and we have that vi, maybe I'll use the colors here, vi vj, and this is going to be vj. So blue component vi is equal to this matrix here, right? So it's equal to vi upper index contracted with this matrix, the very same matrix that determines the law of the scalar product. So you call this matrix Gij. It really deserves a name. And you also notice that this matrix appears here as well as a relationship between covariant and contravariant components. And this matrix is called components of the metric. Metric because it measures something. What does it measure? Well, it measures, through scalar product, it measures the length of the vectors. Although it's not its only role, it also tells you the relationship between the different components. Okay, so this is what we call a metric, and later on, probably you already heard the class, we call it the metric tensor. So this is it. This is the whole thing. What I want you to think about is that if metric tensor, if metric is given by this relationship, then what is this? In other words, what is the inverse of this relationship here? So what is the inverse of, now I'm not going to use colors anymore, Gij Vj. In other words, how do you represent VIs in terms of VI down, contravariant component in terms of covariant components? And this is related to the question that I mentioned before regarding covariant components. The question is, what is the basis of vectors in which I can write V vector as covariant components, as an expansion in terms of covariant components in a basis Vi. So what is this basis? And you can think about it as an exercise, and it is drawable. The picture is drawable, and but it's just gonna add up to your understanding. It's not something fundamental. You may ask me about it if you want. I will tell you about it, but I think this video is it. So how does all this relate to Minkowski space? Why am I writing red? Minkowski space. Well, in Minkowski space we have, if we follow what we just learned, is that E mu dot E nu is equal to G mu nu equal to eta mu nu equal to minus 1, 1, 1, 1. And all the rest of them are zeros. So there are no cross terms, which means that this is an orthogonal basis. Orthogonal basis, but it's a little bit different than Euclidean one because it has this funny component eta 0, 0, which is E0 dot E0 and says this is minus 1. So if you want to think about this literally as a scalar product and try to draw it, if you try to draw it in Euclidean space, it would mean that E0 is anti-parallel with itself. So there is an angle of pi here. But this paradox comes because you think from the viewpoint of Euclidean space. And this is not a Euclidean space. Minkowski space is not a Euclidean space. So this interpretation, this analogy, doesn't make sense. If you ever learn how to draw in four-dimensional space, and if you can bring me there, I would gladly look around and learn how it looks like. But we are unfortunately stuck in three dimensions, in three-dimensional Euclidean space, and we can only interpret or embed inside such spaces and often this can lead to a pitfall in your understanding. So these kind of things, these kind of examples that we had, are good to practice your mind and to massage it a little bit, but also it's good to compare them and to think about what does it mean in terms of more general situations, like in this Minkowski space. And if it brings something like this, then this is a sign that you have to open your mind. This is the sign that you have to think beyond what you thought is the usual thing, what you thought is sort of a dogma. The only dogma here is that E mu dot E nu is equal to G mu nu. This is where you start from if you want to define basis. So this is what defines your scalar product, right? It is these components which tell you what is going to be on the other side of definition of scalar product. If you have a Euclidean space, it will be something. If you have Minkowski space, it will be something else. If you have a general curved space, it will be something most general that depends on coordinates even. So the scalar product depends on where you are. I mean, the scalar product between these two basis vectors. Well, basically, it will mean that you will have some curved lines, right? And then if you draw a basis here, and if you draw a basis here, if you bring them together, like if you bring this basis over here to this point, then there would be a certain offset between the corresponding axes. So it follows the curvature of space. So this metric encodes that. This metric components, they encode that. Okay. Another thing is that those components that we learned, those components, those definitions about covariant and contravariant components that we learned, that V mu lower index is G mu nu V nu upper index, they are the same as they have the same meaning as what we described before. It's different projections, except that different projections in Minkowski space are a little bit tricky to visualize. Maybe one can do that when it comes to space components, but when it comes to time component, then we had that this V0 is equal to minus V0. Okay, and it's minus V0 because there is this metric G00, actually eta 00, V0 there. Okay, and it's the, actually it should be G0, eta 0, 1, V1 plus and so on, but the thing is all these other terms are vanishing because there are no cross terms in the metric, in this metric. In some other metrics you will see, like in GR, there are space times in which you have G0 nu component which are not zero, for nu being a spatial index. And then this relationship would look a lot different. So please think in terms of this relationship always instead of this one, even if you're in Minkowski space, because this will help you think about how to implement the metric. So in Minkowski space you can use eta, but it will help you how to implement the metric when you have an expression with upper indices and you want to express it in terms of lower indices, or the other way around. So this t mu nu with a lower index, if it is a tensor, then you would express it from a double summation over mu over alpha and beta, because there are two indices to lower from t alpha beta. So lowering on each index involves a metric, and raising on each index involves an inverse metric. Okay, I think that's it, and I hope that I was not too boring, or you had a good time laughing at my awkwardness moments that I had. So see you guys in the class, and have a nice day or night or whenever you're watching this. The end.